Welcome, fellow engineers and IT enthusiasts. In today's dynamic world of cloud-native applications, microservices have become the backbone of scalable and resilient systems. But with great power comes great complexity, especially when it comes to understanding what's happening inside your distributed ecosystem. How do you keep an eye on hundreds, or even thousands, of tiny services interacting in real time? How do you know when something's about to break, or when performance is degrading? That's where robust observability comes in. We're talking about tools that don't just tell you if something is down, but why it's down, and how it's performing. Today, we're diving deep into the industry standard duo for monitoring, Prometheus for metric collection and Grafana for powerful visualization, all running seamlessly on Kubernetes. This isn't just theory. We're going to walk through a practical, hands-on example, deploying sample Go microservices, setting up Prometheus to scrape their metrics, and then building interactive dashboards in Grafana to gain immediate insights. By the end of this video, you'll have a complete, functional monitoring stack and a clear understanding of how to implement it in your own Kubernetes environments. Get ready to bring clarity to your microservice chaos. At the heart of our monitoring solution lies the powerful combination of Prometheus and Grafana. Prometheus, often referred to as a monitoring and alerting toolkit, acts as our time series database. Unlike traditional monitoring systems that wait for data to be pushed to them, Prometheus operates on a pull model. It periodically scrapes metrics from configured targets, which in our case will be our microservices. These metrics are numeric data points recorded over time, like request counts, error rates, or CPU utilization. It's purpose-built for the dynamic nature of cloud environments, making it ideal for microservices. Then, we have Grafana, the visualization powerhouse. Grafana doesn't collect data itself. Instead, it connects to various data sources, including Prometheus, and transforms raw metrics into stunning, interactive dashboards. Think of it as the ultimate storyteller for your data, turning complex numbers into intuitive graphs and charts that help you quickly understand the health and performance of your applications. Together, they form a symbiotic relationship. Prometheus collects the rich, detailed telemetry, and Grafana presents it in a way that allows you to make informed decisions swiftly. This separation of concerns, collection versus visualization, is one of the key reasons this stack is so popular and effective. To demonstrate this setup, we've prepared a simple yet effective sample application. It consists of two basic Go microservices, aptly named Microservice A and Microservice B. These aren't just any services, they're designed with observability in mind. Specifically, they expose Prometheus metrics on a dedicated /metrics endpoint. Inside the sample app /main.go file, you'll find how standard Prometheus client libraries are used to define custom metrics, such as http_requests_total, a counter that tracks the number of HTTP requests, and last_request_timestamp, a gauge that records when the last request occurred. This instrumentation is crucial because it's how your applications communicate their internal state to the monitoring system. Furthermore, when we deploy these services to Kubernetes using the manifests in the K8s/directory, you'll notice specific annotations on their Kubernetes service objects, like prometheus.io/scrape, true, and prometheus.io/port, 8080. These annotations are not just metadata. They are key signals that Prometheus will use for automatic service discovery, telling it exactly which services to monitor and on which ports. It's a clever way to integrate monitoring directly into your Kubernetes deployment strategy without needing manual configuration for every new service. Before we can deploy our monitoring stack in microservices, we need to ensure our environment is ready. First and foremost, you'll need a running Kubernetes cluster. Whether it's a local setup like Minikube or Kind, or a managed service like GKE, EKS, or AKS, the principles remain the same. Alongside your cluster, you'll need kubectl, the Kubernetes command line tool, for interacting with your cluster, and Helm, the Kubernetes Package Manager, which we'll use extensively for deploying Prometheus and Grafana. Finally, Docker is required if you plan to build the sample microservice images locally. The first practical step involves building these Docker images and making them accessible to your Kubernetes cluster. Our project includes a Docker file within the sample app directory. We'll build an image tagged local registry/sample microservice, latest. If you're using a local cluster like Kind or Minikube, you'll then need to load this image directly into the cluster's image cache, avoiding the need for a remote registry. For remote clusters, the standard practice is to push your image to a container registry like Docker Hub or Google Container Registry and then update your Kubernetes deployment manifests to pull from that registry. This foundational step ensures our sample microservices are ready to be orchestrated by Kubernetes. With our custom microservice images built and accessible, the next step is to deploy them onto our Kubernetes cluster. We've provided Kubernetes deployment and service manifests for Microservice A and Microservice B within the K8s/ directory. These YAML files define how our services should run, including details like replica counts, container images, and exposed ports. What's particularly important here are the service definitions, which contain special annotations like Prometheus.io/scrape, true, Prometheus.io/port, 8080, and Prometheus.io/path/metrics. These annotations are Prometheus-specific and are crucial for its auto-discovery mechanism. By applying these manifests using kubectl apply fk8s/, Kubernetes will create the deployments and services, making our microservices accessible within the cluster and discoverable by Prometheus. After applying the manifests, it's always good practice to verify that your pods are in a running state using kubectl get pods, lapp equals microservice A and kubectl get pods, lapp equals microservice B. This ensures our applications are up and ready to expose their metrics for collection, laying the groundwork for Prometheus to begin its work. Now that our microservices are running and exposing metrics, it's time to bring in Prometheus. We'll deploy Prometheus using its official Helm chart, which simplifies the installation and configuration process significantly. First, we need to add the Prometheus Community Helm repository to our local Helm client, followed by updating our repositories to fetch the latest chart information. The real magic happens when we execute the Helm install command. We'll install the Prometheus chart into a dedicated monitoring namespace, which helps keep our observability tools organized. Critically, we'll pass a custom values file, Prometheus/prometheusvalues.yaml, to this command. This YAML file is where we define how Prometheus will discover and scrape metrics from our microservices. Without this custom configuration, Prometheus wouldn't know where to look. Once the Helm command completes, Kubernetes will provision the necessary deployments, services, and other resources for Prometheus. We can then verify that the Prometheus server pods are running correctly within the monitoring namespace using kubectl get pods, and monitoring, lapp equals Prometheus. This confirms that Prometheus is online and ready to start collecting data from our meticulously annotated microservices. Let's take a moment to demystify the Prometheus/prometheusvalues.yaml file, as it's the core of how Prometheus intelligently discovers and scrapes our microservices. Within this file, we've defined an extra scrape config section, specifically a job named Kubernetes Services. This job leverages Kubernetes service discovery, meaning Prometheus will actively look for service objects within the cluster. The relabel_configs are where the filtering and transformation logic happens. The first rule ensures that Prometheus only scrapes services that have the Prometheus.io/scrape, true, annotation. This prevents it from trying to scrape every single service in your cluster. The second rule further refines this by targeting services with the app label matching Microservice A or Microservice B, focusing only on our sample applications. Subsequent rules dynamically set the ___metrics_path__and__.